Okay, our next topic is the non-negative matrix factorization. This we'll get to see some more things in nonlinear programming, optimization method, and we will come back to that alternating gradient descent method. Okay, so this was a talk, again, a long time ago, but I've done some consulting for Yahoo and SAS, statistical software company. So I did my graduate work at NC State, and right in the back door was this SAS software company, which actually was developed by two graduate students at a graduate student and a professor at NC State. And they both took a leave of absence and then made this company that now has an entire campus, its own campus. And so what a little bit of code can do. My mentor at the time at NC State, Carl Meyer, professor of mathematics, taught linear algebra and matrix analysis. And he said he had these two in his class. And at the end of the class, the student came up and handed him a stack of like computer printout. That was when it was on like green and white paper, like handed him a stack like that big on his desk and said like, look, I coded every algorithm you taught us in linear algebra in this class. And my mentor, Carl Meyer, has written a book that's about 1,000 pages on linear algebra and matrix analysis. My favorite textbook, actually, check it out. Carl Meyer, Applied Linear Algebra and Matrix Analysis. Changed my life. Actually, a couple pages in the book changed my life. And made me start doing the research that I was doing on information retrieval. So anyway, being in the backyard there, they went and made, I lost my train of thought, got off on tangent. So Carl Meyer, that student came up and slapped that computer printout, and Carl thought to himself, oh, well, great, but kind of what's the point of that? Well, that was the start of SAS. That very summer after that, his class, that student took a leave of absence, the professor took a leave of absence, and they built a software, statistical software that within it, did a lot of statistical things, but within that, they needed a lot of linear algebra code, which you saw from the simplex, you saw that from interior point method, like so much of that is built on basic things in linear algebra, matrix multiplication, projections. Sherman-Morris and Wordberry when we got advanced with the revised simplex. So being that they were in our backyard and Carl known them, we had done consulting. They asked us to come over and teach them some stuff about text mining. They had just started a new text mining group. So this was like early 2000s, and I did it probably through 2010 or 12, consulting for SAS. I go out there when I was living in Raleigh, much easier, like every couple of months and give them an update. And then since I moved here, maybe every semester, and teach them some things about text mining, build up that group, which was at the time just a couple of people, and now it's a much bigger group. And they have many procs, which is the SAS thing, a built-in command for running things. And several of those, they've implemented our algorithms for the non-negative matrix factorization. So, and this was a talk I gave at Yahoo. I'm going to skip a lot of it and just kind of get to the essence for y'all and tell you what the non-negative matrix factorization is. It relates to text mining and data mining, and there's some classic ones. So if you took my Calc 3 class, you learn a little bit about the vector space model. If you take 452, 552 next semester, depending on the makeup of the class and what we want to learn, we'll probably do a good bit of text mining. Students seem to really like that. The vector space model, this is from the 1960s and 70s. Gerard Salton was a Cornell professor, invented this thing called SMART, System for Mechanical Analysis and Retrieval of Text. And we will have a matrix that we're going to call a term by document matrix. And each document is a column vector in that matrix. And the ij element of that matrix is the number of times term I appeared in document J. So, go through the dictionary, there's around 400,000 words in the English language. So finite, big but finite. So M is about 400,000. And let's say you have a document collection of 1,000 documents. Maybe these are scraped from Amazon reviews. A lot of times there's well-controlled document collections. These are the abstracts of all documents in the Medline database, the abstracts of papers in the aerospace engineering journals. So there'll be, and also is finite, but you can also create this for the World Wide Web, right? We'll be talking then, maybe you're doing it multilingual and it's much bigger, or just English language is 400,000, then there's like billions of documents. So it can be done. It's going to be sparse though, because not every document vector uses every term. And then what you do once you have this, you create a query vector, like maybe you want to search on in that medical example, maybe there were 1,000 documents pulled from the abstracts of a medical journal, and you want to search on heart disease or something. So you'd make a query vector that turned on a 1 in heart and a 1 in disease, and it was zeros everywhere else. And then to retrieve information, you get the angle between the query vector and every document vector. So you're getting a cosine angle, 2 vectors, all these document vectors, my fingers, and then let's say that my pencil is a query vector, and you want to get the one that's closest in angle. That's cosine measure, you can do that. So here it is. It's really just inner product, and then we're normalizing. So ON worked to do that. Later on, this woman at IBM, Susan Demes, came along with a better way in the 1990s to do to take A and actually do a factorization of it. So single value decomposition, something you might have learned at the end of linear algebra, just like an LU or what's the other one you do? Oh, a CUR, or probably though you remember an LU, but it's a type of way of decomposing a matrix into other matrices. This one decomposes in 3 matrices. Those matrices usually have different properties depending on the decomposition. So that's the general idea there. I'm just not going to go into too many details on that, but that improves performance. It's a much better way of doing it. It's called latent semantic indexing. Maybe we'll do more on that next semester. Lots of other decompositions you could use. Another woman, Tammy Kolda, came up with the semi-discrete decomposition, which is a way of decomposing A into these 3 matrices where X is only made up of -1, 0, and 1. So hopefully you can see that there's some sort of optimization going on, because you want to find the X, D, and Y matrices that are closest to A with a constraint that X has to have. X and Y are matrices made up of these components. So she's actually solving an integer program when she does that. Okay, but all of these methods start with an A matrix, a term by document matrix A. That is the number of times a term appears in a document. So it's a non-negative matrix, and they decompose it into elements that might be mixed in sign. They can have some negatives in here. So that makes it difficult to interpret. And what happened is these guys, Lee and Son, came around in 2001, I think at MIT, and they said, well, what if I could decompose it? So again, A is non-negative. Instead of decomposing it like Susan Demes said with the LSI into these 3 matrices, of which this one's mixed in sign, this one's non-negative, this one's mixed in sign, the sign values make it hard to interpret. What does it mean to have a negative negative element here? Is that the negative number of times a term appears, or does it mean to be negatively correlated with the word? So these guys came up with a new decomposition and an algorithm to create that. So their decomposition uses 2 matrices called W and H. And it's had so many uses since. You can't patent an algorithm, but you can patent an algorithm applied to an application, a particular topic. And many people have taken the NMF and applied it all over the place, gotten patents for it. Okay. The nice thing again about the NMF is that you can do this decomposition. So if I'm looking at a particular column of A, it'll be decomposed into W and then a certain column of H. And really you can think about that as a column vector in A. So a particular document, document 11 in that Medline collection of medical abstracts, can be decomposed and built from these basis vectors W with these weights H. So you can say how much does the basis vector W, and we're actually going to call them topping vectors, because it turns out, because they're non-negative, they correspond to terms that seem to cluster around, these terms are clustered around topics. And then there's a weight associated with it. So it's like, if this was a really big weight and that Medline document is a lot about this topic vector, and if this weight's really small, then it's not much about that topic vector. Those guys, Lee and Sung, used it to do some image processing, and what they found, the difference between what existed with the SVD and what they were doing with the NMF, was that you were getting a parts-based interpretation, is what they called it, of the image. So here's the original image, not a great image, kind of cloudy, but you're going to decompose it, and this is the W matrix, and this is the H matrix. And this is what we get back as our approximation. And we'll see that the W matrix is actually, when you zoom in over here, built up of parts of a face. So you have a collection of a bunch of faces, and we can decompose those into parts. Like here's some eyes, there's a left ear, a right ear, a hairline, different hairline, eyebrows. And it's like you take this much of a particular part and it builds it into the face, as opposed to what is called with the SVD, they usually call these eigenfaces or singular faces. Like here's the most important component and it looks a lot like a face. The next one, what the heck is that? It's hard to say, but you take a little bit of this one and a little bit of that one, and maybe more of this one, and so on, and you add those up and you get the image back. So this interpretability is what made Lee and Sung's NMF so useful. Things you can do for image mining: you can use it to compress data. You can use it to find similar images. So here's like the original ones, and then they're compressed and stored much less, and of course not as accurate, but much less storage. You can cluster images. You can find similar images as well. So you can do like a database and query it, all with the NMF. Here's the example of that med database. If I used a compression of the data first and built my basis vectors, you can see that like here's a whole topic about heart stuff. Here's one about like blood pressure stuff. Here's one about kidney things, all those terms. Here's children and autism. So these are topic vectors. Within that data set of 1,000 Medline abstracts, these are the main recurring themes. These are the topics that seem to come up. And so I can take, say, document 11 and say, oh, actually, it's talking about children and autism, and sometimes maybe a little bit about their blood pressure, let's say. So it would be built largely from this one and a little bit from that one. Here's just another example that you're building. These are the 4 basis vectors in W. They actually correspond to these terms. These are the H weights. It uses the first one a whole lot, the next one a little bit, and doesn't use these at all to build the document, a particular document about the Constitution of the United States. That makes sense. Like it's a lot about, uses the president and Congress and power, Constitution. So you can see how those two would contribute and these two would not. Okay, so these sorts of decompositions, the LSI, the vector space model, the NMF, same sorts of things in text mining. You can compress your data and store it better. You can find similar terms, find similar documents. You can cluster terms, cluster documents. You can track topics. People have used this for the Enron email data sets. There's some interesting things I've done with collaborators. You can use it for purchase history. Like, again, if you're Amazon, you're collecting data like this, which is a non-negative matrix, is like the number of times user 1 purchased item 1, number of times user 2 purchased that item, and so on. So you have a non-negative matrix, and you could factor it in the same way, LSI, vector space model, or NMF, and do these sorts of things. You can create profiles for your classes of users, find similar items. Okay, but what does all of that have to do with optimization? So here we go. So here was the Lee and Sung problem. Now this should look like things from our class. They're trying to minimize, they have a data matrix A. So this is matrix of constants. What they want to find is the W and the H. So they're saying, find me a W matrix and an H matrix that is close as possible to A in some norm, they're doing something here called a Frobenius norm. They want to minimize that, right? Because they're doing as close as possible, subject to the constraints that W and H, those matrices, every component, every IJ has to be greater than or equal to 0. So they use what's called a mean squared error, but there's other errors you could use. They made an algorithm that did this, and it actually just finds a local extrema of this, but the local extremas give great results and seem to work really well. Notice that this optimization clearly nonlinear because your two variables are multiplied together. For us, this would have been like in our Tory textbook problems, this would have been like an x1 times an x2, but instead we have way higher dimensional because we have actually an entire matrix, a W11 times the H11, a W12 times the H21, and so on. All those are multiplied, makes it nonlinear. Now it's convex in one variable or the other, but not both, which makes it, would be nice if it was convex, right? Because every local extrema is a global extrema for a convex programming problem. We don't have that, we're not that lucky. But the fact that it's in one or the other makes the alternating algorithms that we've talked about work really well. Again, huge number of unknowns for this, right? W, it has dimensions M by K, H has dimensions K by N. So here's an example. If A was 70,000 by 1,000, so 70,000 words we're interested in. English language, maybe the most common word, 70,000 words times 1,000 documents. And you have just 10 topics you're trying to get. That's 800,000 unknowns. And that's actually a small NMF. NMF can be done on much, much bigger problems. It's surprising how well it works, right? I mean, it's an enormous problem. And again, this objective function is just one of many. You can really toy with that, optimize, tweak it for your particular, customize it for a particular application. But as usual with nonlinear programming, convergence to a local min is not even guaranteed to a local min for any of the algorithms. Tons of algorithms exist. I've contributed some. I worked with Mike Berry and Bob Clements, and we added one here in 2005 that actually became one of the most cited algorithms for NMF. And then working with SAS, I created these two, alternating constraint least squares and alternating, I think, Hoyle constraint least squares. So I'll just show you a little bit of those. Lee and Sung, this is really the algorithm that they're doing. It's pretty basic, pretty simple. Not many lines in MATLAB to do this. This dot star means component-wise multiplication in MATLAB. So you could code Lee and Sung yourself with a few lines of MATLAB code. Notice the work per iteration. It's lots of matrix multiplications, but that's about it. I mean, component-wise is O(n) squared, matrix multiplication, O(n) cubed. So O(n) cubed in every iteration. Converges to a fixed point, that's all you can say. So it could be a stationary point. In practice, though, it seems to work great. Lots of other ways you could improve it. You could demand that it be sparse. Like I want W and H to also be sparse. A is typically sparse. What can I do that makes W and H sparse? This was a great contribution by Mike Berry and Bob Clements, and I helped on that one too. This guy Hoyer made some other sparsity measures. Okay, here's how you can make H sparse. We've seen this before with like the penalty function when we talked about interior point methods and the log barrier methods in 7.4. We just briefly mentioned it. Here's an example of where you're throwing something into the objective to be a penalty because you want to reduce the norm, which will make it sparser. You're hoping this is going to help you make H sparser. It's not guaranteed to, but it seems to do in a lot of practice. Okay, then let me just show you one or two more of the alternating ones. Okay, so alternating, yes, okay, let's do this one. This is where we're going to say if I could fix H, and I'm going to initialize it at some, maybe this is the art of it, the smart initializations. I'm going to fix H and find W. So if I fix H, A is fixed, H is fixed, I just need to find W. Well, now it's a convex problem and it's easy to solve that. And actually this is what's called a least squares system. It looks, you know, maybe not as familiar as you're used to. You're used to solving AX equal B, matrix A, vector X, vector B. with at least squares. A transpose AX equals A transpose B. Well, that's really what's happening here, but there's another matrix instead of a vector. So I'm finding W, I'm fixing W and solving for H in the first one. And then the second one, I'm fixing H and solving for W, right? So this first line, W and A are known, W and W transpose known, identity known. This is a scalar, so I'm solving for H. Once I know that, I fix H down here, fix H, A is fixed, solve for W. And I just keep flip-flopping like that. This was the example of what we talked about last talk when we had an X1 and X2, and you fixed an X1 and moved in the X2, fixed the X2, moved in the X1 in an optimal way, fixed the X1, moved in the X2, and you could do that rectilinear movement until you got to the extrema. That's really what's happening here in way higher dimensional space because these are matrices. Pros and cons of these algorithms, again, conversion difficult thing. In fact, for this algorithm, this is a more advanced algorithm, but same idea. It's an alternating, fix one variable, find the other, and just keep flip-flopping. It's hard to prove convergence if this is going to even go to a local min. It might go to a stationary point, and yet in practice, it works so well. This one was actually tough to get some referees to approve because they wanted to see the theoretical results. But we started having a lot of empirical results because we had partners with SAS, and people around the world were emailing just saying how much they love this algorithm, how fast it was, how simple. It did make sparse outputs. And once it was published, that actually became the top cited article in that particular journal. So it's just to show you that like there's a theory and practice, right? There's a gap there, right? And in practice, this has been so helpful for folks. In fact, it became a proc in SAS, and it became a built-in command in MATLAB. So if you run MATLAB's non-negative matrix factorization command, which I think is NMF, if you do that at the bottom where they give the references, that'll be to Barry et al. And Barry is the colleague that was. So our paper is what built their proc in both SAS and MATLAB, because it is fast. Like there's other good algorithms that have some convergence, a little more convergence things they can say, results that they can say, but ours is fast and sparse. Okay. Okay, yeah, so this is still an open question. I mean, people are still working on this. Like, can you initialize? Ours was an alternating least squares algorithm. Well, you have to initialize. What's the initial H matrix you want to start with? There's smarter ways to do that. Might make it faster, might make you have a better chance of getting to a better local extrema. Maybe for the text mining, here's a big area of research in what's called updating. For the text mining example, maybe you get a new document in, or every month you are crawling the web and you find 100 new web pages, or 100 new Amazon reviews that you want to add to your database. Do you need to redo the NMF completely from scratch? You just did it with an A matrix that looked very similar to this A matrix. So think about what we did with the revised simplex. Something very similar happens here. That's called updating the NMF. Can I just fold in those, say, 10 new reviews that I got to the 1,000 that I already have and compute the NMF faster? Yeah, different objective functions you can choose. So a lot of work has gone in there. And then just some extensions, like whenever you're doing research, you should say what else could be done. It doesn't mean you'll get to it, but you could make a call to the community. So some people are looking at more ways to factorize a matrix. Like we got a W and H, but maybe we could get many more matrices that factorize it. What does each of those mean? Oh, and then like doing this on the web, something in the web scale, could you do that? Where these are terms, and then this is a particular web page, and maybe the number of terms in the anchor text from one to the other. Okay, I think that's enough main ideas there for the NMF. It's a nonlinear program. Convergent theory is hard, but in practice, you can make algorithms that do things. Often the fixing one variable, finding the other, works well, that alternating gradient descent scheme. Okay, a few more talks, one on, I think, evolutionary optimization and then multi-objective.